Hello, my name is Lucas Venta and I am one of the doctoral candidates of the GECKO Doctoral Network. My project is about immersed isogeometric analysis of phase field modeling, and in this video I will try to give a brief overview of the topics I'm working on. One of the main ingredients of my research are the so-called phase field methods. These methods reinterpret an a priori discontinuous interface as a smooth and continuous field. And actually, they have found many practical applications in many fields, such as the modeling of tumor growth, crack propagation in the context of fracture, phase transitions, and a very long etc. However, one of the challenges of phase field modeling is the fact that one needs to have a very fine discretization across the phase field in order to be able to resolve the steep variation between the phases. The most straightforward way of achieving this fine discretization would be to perform a tensor product refinement. However, this introduces additional degrees of freedom, which translate in higher computational costs. The way we tackle this problem is to first break the tensor product structure of B-splines, which are the shape functions that we use in the analysis, and to also be adaptive to in order to be able to track the evolution of phase field, meaning we will be able to not only locally refine, but also to change the mesh as the phase field evolves. My first steps in the project have been regarding or in the direction of implementing high order PDEs in the isogeometric analysis framework. And more specifically, I implemented the canhilliard equation in its primal form within the Gizmo library. In the slide, I'm showing already the results in a 2D patch where we see that the mesh gradually changes as the phase field evolves, just as we wanted it to be. Of course, the extension to 3D is also possible, and you see that now we coarsen and refine the three-dimensional elements as the phase field evolves, and also we, as expected, have fine meshes to describe the phase field and coarser meshes in the areas where we have the equilibrium concentration. Now, all of the geometries I've shown are the easiest geometries we can think of in the three-dimensional case, which are cubes. And they are, of course, also single patch geometries. But we wanted to take a step further and try to solve the canhilliard equation on a more complicated geometry. And for doing so, we took a single patch parametrization of the DAC and tested our code against it. We were very happy about the results, but again, this is a single patch parametrization, and what one finds in real life CAD designs are multi-patch representations of the objects. This is tricky because multi-patch representations require the imposition of continuity requirements across the patches in order for us to be able to solve the high-order PDEs. And besides, CAD representations come in the form of boundary representations. So we also need to take care of volume generation and so on. For this reason, we are motivated to go from a body fitted approach to an immersed approach. And among the immersed approaches or embedded approaches there are in the literature, we are interested in the implementation of the finite cell method, which put into very simple words, essentially embeds the geometry that we want to compute on a background mesh, and introduces as well an indicator parameter alpha that indicates whether we are inside the solid or outside of it. This method has proven to be super successful to represent even very intricate geometries, such as the one that I'm showing in the slide, which is a microstructure of a bone, which is why we are quite excited about it, and we think it has a lot of potential for the applications that we are dealing with. With that being said, I want to thank you for your attention, and I want to encourage you as well to keep up with the news from the network, since I think very nice things are coming up soon. Ciao, ciao. Thank you.